Hello, I'm Richard Hooper. Welcome to today's webinar titled Unified Software Defined SAT/Ground Solutions, Magic of AI and 5G. Now, our speaker today is Amir Kashinazadi, Systems Engineering Manager at Spacebridge. Amir has spent the last 20 years at the edge of high tech, working as a system designer, architect, and project manager in satellite communications, telecommunications, and network. Amir will be talking for around 45 minutes, and then we will have a short question and answer session. If we cannot answer all the questions at the end, we will follow up post-event. Please use the Q&A function at the bottom of your screen. So without further delay, I will hand over to Amir. Welcome, Amir.
Thank you so much, Richard. Let me just share the presentation. Okay, first of all, thank you everyone for participating in this webinar. I hope it will be useful. We're talking about the unified satellite system to the ground as one system for all. This webinar is going to have two sections. The first section, we're talking about the new generation of the satellite, the new technologies are coming up in the next 2-3 years. And on the second section, we say, okay, what can be done about that? So, around 15 years ago, I remember everyone believed that commercial use for satellites is going to die, and there's no market for that anymore because terrestrial network is growing fast and satellite is too expensive. But at that time, HTS, high throughput satellite system, changed the scope. So they got the market with much more reasonable pricing. And the footprint of the commercial satellite has been there since what? Now, in the last 2-3 years, we've heard a lot about the new LEO constellations. They're beautiful, and there are many players into that. And they also believe that, okay, the LEO is going to kill the GEO, the application for GEO, and get all the markets. But now, because of many reasons that we are going to explain, we'll see a new kickback is coming from the very high throughput software-defined GEO satellite systems. So apparently they are winning the game again over the LEO. First of all, let's talk about the LEO satellite systems. We are facing two generations. Generation one is pretty classic. It is steel bent pipe. However, the payload is mostly digitized. So there are some capability of the software-defined satellite network into that. There is an inter-satellite communication and very high symbol rate and vast coverage. Of course, not vast coverage with only one satellite, because we're talking about LEO, not GEO. So what we're talking, just a quick explanation. The LEO distance of a satellite to the Earth is around 500 to 2,000 kilometers. The GEO is 36,000 kilometers. So the LEO is rotating much faster than the Earth rotation. It means an object on the ground will only see the satellite for 3 to 10 minutes in 24 hours. So to have a vast coverage, there should be multiple satellites in the orbit to hand over and take care of the rest, take care of the traffic. The GEO is different. The GEO speed is exactly same as the Earth rotation. So the object on the Earth will always see the satellite at top. However, 36,000 kilometers means a very long round trip delay. So it's not very great for real-time, non-jitter and non-delay tolerant applications. The second generation of the LEO is going to be onboard processing. It means that the data is going to be demodulated and decapsulated, and there is a path finding for the data, for the individual data on the satellite. So the satellite from a terrestrial network looks like just a node, like a switch or router, which is amazing. However, it has its own challenges. So it provides better telemetry data, controlling data, but how it's very complex on management. Here you will see we are having many landing stations, virtualized data processing, point of presence, and virtualized management system. So There are many players into LEO, new LEO constellations. They are mostly consortiums working together. They're making closed networks. In Canada, we can name Telesat as the biggest one with Lightspeed. Kepler is a smaller startup company growing very well, and they have their own niche market working on that. You will hear, for example, Amazon Kuiper is absent here. It's the biggest one. So they're going to have 44,000 to 46,000 satellites on the orbit. And SpaceX, these days you hear a lot about SpaceX, especially about providing coverage for Ukraine and the advertisement around the SpaceX. So just to show some of these challenges, we've taken SpaceX as an example, and we'll describe what are the difficulties with that. Let's come up with an example. We want to have a full coverage 24 hours over the United States. With SpaceX Gen 1, we will require 4,000 LEO satellites. It's not a small number. So the constellation requires 4,000 satellites to have a full coverage. But not only to that, because the landing stations, the ground segment require to be in a certain distance from each other. So we'll require 132 teleport locations and with 3,200 ground-based tracking antenna. So you will see what you need on the ground is massive. And what we call it CapEx, capital expense, is too high to working on this actually system to have a full coverage on a large country size. So sometimes there are advertisements that's okay, SpaceX is going to provide coverage for this country or that country. It might be true, but it might not be true as a 24-hour coverage. The other advantage of the LEO over GEO could be the launching cost. Launching cost in LEO, because of course, much shorter distance is less than $1,000 per kilograms. The GEO is plus $50,000 per kilograms. However, you need to actually send much more LEO satellites to have the same coverage. The weight is another factor. Gen 1 is 575 kilograms. It's pretty light, really decent. But the Gen 2 is 2750 kilograms, which is pretty high. And we will get to the weight of the new GEO satellites, so you will see this number is not really a lightweight satellite. But why we are saying that, okay, GEO, the next version and next generation of the GEO is still having its own market, and LEO might lose some markets to GEO. First of all, because the LEO's constellations are very complex in nature. The management, the constellation management is crazy. We are facing hundreds and thousands of satellites on the sky. There is a handover, Doppler shift, and Doppler shift with mobility is even worse because we have a Doppler shift, Doppler effect from the satellite movement and another one from the moving object on the ground. The jitter mitigation, because the satellite is getting closer and further from the object to the object and from the object on the air. So there should be a mitigation for jitter. So CapEx, we really don't have numbers for CapEx because it really depends on the system, but you've seen in the previous example that there are requirements for many landing stations, many teleports. But the OpEx is definitely going to be costly because this constellation management, all these numbers of landing stations, so the operation is going to be costly. We explained it requires several teleports. The implementation is not so easy. High cost of the terminal. Terminals are coming with phase array antenna. Phase array antenna is pretty expensive, so we cannot really say it is for consumer markets. The other issue is interoperability. So all these LEO constellations, they are making it completely as a closed network with their own technology. There is nothing open, there is no interoperability, and this is a risk factor for the satellite operators. And finally, I don't see any solution for massive broadband and consumer market on these satellites. For IoT, when we talk about industrial IoT, because there are several categories, For some of them, LEO is a good solution, but for some others, the LEO is not a solution, especially if they want to transmit emergency data or alarms or something like that. So they need a full coverage over 24-hour and with very cheap terminals. So that's the reason probably these LEO systems are not really a good candidates. But what we are facing right now, okay, we said the complexities and challenges with LEO. What's the counter offer? It's a software-defined, very high throughput satellite on GEO. The scale is very high throughput satellite. It means that we are having several beams of 500 megasymbol. So it means terabits of seconds capacity. Since it is GEO, so it's going to be multi-mission, so it can have diverse markets there. But what is really interesting on this software-defined satellite network are not those. They were already in the market. It is a dynamic change and adaptation of the beams, frequency plan, and power on the satellites. So the resource allocation, the beam forming, the frequency planning, everything could be dynamically changed on the satellite. And there is a fast link to the ground. So the ground segment can order the satellite to implement the change. However, there are multi-layers from the, let's say, 3-4 layers of virtual to the physical layer. So the virtual layers are, I would say, more faster to change. So they could change on real-time basis. The physical layers, it's not that fast to change, but we can also change the physical layer. We can change the spot beam to white beam, change the beam size, and also beam chasing feature that they are introducing and the players are introducing. So the beam can chase an object on the ground or, for example, an airplane or something like that. So these are the biggest advantage of the software-defined satellite network and GEO. There are 3 major players. There are other players, but these 3 are dominant right now on this technology. This is Thales, Boeing, and Airbus. Just let's take a quick look at them. Thales has Space Inspire, started in 2020, supposed to be delivered in 2024, 2025. They've already got some customers, Intelsat, Arabsat, Astra, and SES. It's an ESA, European Space Agency Partnership Program, which is a very good sign. So what they claim, first of all, instant in-orbit adjustments. So all the changes would be done instantly over the fast link to the satellite and fully programmable. Less weight, higher capacity. The weight is pretty good. It's 2,000 kilograms. No, the GEO satellites, the classic one could be up to 5,000. So 2,000 is a really good number. As you notice, it's even lighter than LEO Gen 2 of SpaceX. The other player is Boeing 702X. They're building the GEO variant based on their knowledge and experience on the O3b mPOWER. It was 702, so they delivered 11 MEO satellites. So they are still trying. They are also trying to be smaller and faster to build and also smarter. So having a digital payload, which is adjustable and adaptable. The weight's gonna be 1,900 kilograms, which is pretty good. The last one we're talking about is Airbus OneSat. Airbus OneSat started 2019, supposed to be released in 2023. They already got some customers, Inmarsat, Intersat, Optus, and JSAT. It's pretty heavy. It's around 3,000 kilograms. It is, again, another ESA partnership program. What they claim is pretty nice to, as a marketing point, it's pretty nice. They said it's 50% less time to market and 50% less total cost of ownership, which is pretty attractive, honestly, and 100% flexibility. So they're going to make it faster to build and, of course, less costly to operate, to have it. What does it mean on the ground segment? On the ground segment, it means we will have multiple landing stations, as you see here. It's either distributed or centralized. It means that encapsulation, decapsulation could be at the landing station, or no, could be separate. Data processing is going to be virtualized, preferably, but it's going to be centralized outside of the teleports. Management system, the same. There would be several beams, very high throughput satellite in a scale of terabit per second, geographically diverse gateways, software-defined network for the networking, and SD-WAN is possible on these networks with the features of chasing beam mobility and dynamic load balancing. So let's see what we can do to achieve such a purpose. We are thinking about a unified satellite ground solution to provide three things: the best of user experience, the link quality, with all this telemetry data we have, with spectrum monitoring, the best in interference mitigation and dynamic beam changing, white to spot and changing the size. Also to have a dynamic adaptive coding modulation and uplink power control in open and closed loop. Also providing the guaranteed SLA, maximum reliability, so not wasting bandwidth on the guards and trying to get the best use of the bandwidth, all the power on the satellite, and also provide the best user experience to the users. So we are required to do some congestion management and mitigation, and this is pretty easy right now because we can change the beam size. And diversity, beam transport stream, site, and gateway diversity. So if there's a failure, the traffic can be rerouted to another transmission or reception means or another beam almost seamlessly. So that's a big advantage. And the virtual network operation is also going to change a lot. So far, the virtual network operation operators could only use a physical or virtual resources on the ground. So, but now we can even give them resources on the satellite. We can assign partially or a whole beam or a couple of beams to a virtual network operator. So to do all these things, SpaceBridge came up with a new idea, which is called VSAT New Radio. What's this beautiful name, VSAT New Radio? There are, beside all those things that we know that the ground segment has to do, let's say high throughputs, handling multiple beams, capacities, mobility, all these things, there are two major, I would say, state-of-the-art aspect to this design. The first of all, it's a ground segment which is adapted to 3GPP 5G. We'll explain more about that, but it's a great way to migrate to the cloud base. 5G is already so advanced in that. So virtualization is and universal and centralized orchestration is another advantage of 5G. And advanced control layer, mobility, handover, these are experiences there. The second one is AI DRM, artificial intelligence dynamic resource management. So in our design, there is a brain, there is a core to decide about all the resources, depending on the situation and on the demand at a time. And this is tailored to the software-defined satellite network. So there's no satellite ground segment entities anymore. There's only one system, which part of that is on the ground and part of that is on the satellite. And they are treated as a whole system. So we don't separate them anymore. It allows us to have a very highly scalable and high throughput architecture. And also it comes up with a feature of having multi-functions, multi-satellite, and multi-orbits. We'll get to these two topics in detail. What's the point? The point is the satellite engineers have always been in their own world. They didn't want to learn from the other technology domains that they have been probably more advanced than satellites. But now I think it's a time to, instead of reinventing the wheel, we start learning from the other markets that are more advanced. Of course, cellular backhauling is much more advanced on some aspects. So the 5G core is pretty interesting and mature system that we can use the technology on the satellites. The second one is AI, artificial intelligence, is going to be more used these days in addition with machine learning. And we will see, okay, how we can use all these things instead of recreating them from scratch. What is AI DRM? We are expecting very clear advantages from this AI DRM. First of all, as I said, it is a brain to control all the resources according and based on the situation of that moment in the network. So guaranteeing link quality, best efficiency, and best use of bandwidth. This is the target. Of course, when we do this best efficiency and best use of bandwidth, imagine just we don't have all the, let's say, 2-3 dBs guard bands all over the network, because we can utilize the network to the best of its own. So you will need a less costly RF there. And because you don't, you are actually using 100% capacity of your network, you will save millions of dollars on OpEx over a year in a large network. But how? To have a core, to have this brain to enforce logical and physical resources configuration, not only to the ground segment, but also to the satellite system. We'll explain a little bit about this. What are the tasks we are expecting this AI DRM to do? First of all, it has to have the optimum configuration, the frequency plan, the beam configuration at a time, on size and power, on the satellite and on the ground. First, the second is a mobility, commanding the mobility. For example, it can sense that the airplane is going to, the airplane in flight entertainment, they can have hundreds of gigabits of traffic. So if they move from one beam to the other beam, first of all, there is a huge handover mechanism. They may get traffic interruption. The second, when they go to the next beam, they will congest the next beam. So they can kill all the regular users on that beam. So this chasing beam is this provides this advantage that the beam, actually this AI core, can command the satellite to chase, for example, this object. Physical resources and logical resources are created and assigned and adjusted, and the SLAs are assigned to the terminal. So there is a scheduler. The scheduler is going to assign capacity and slots to the terminals. And it can also handle the most sophisticated interference and weather condition. There is an open and closed loop ACM and uplink power control, and we don't control it only from the ground. What we are going to do is this system, because it has control over the satellite power, it's going to adjust the power on the satellite first. If it's not enough, then it goes to the ground and it goes to the more protected modulation and coding. Because right now, what we do, right now we are blind to the satellite. We just try to correct ourselves on the ground. So we go to the more protected modulation and coding, but the problem is that we are losing efficiencies. With this mechanism, the correction is started from a point that it is less defective to the network, and after that, if it is not compensated enough, we'll go to the ground. But how? Okay, this AI core is going to do brilliant things, but how? Of course, it cannot do anything without the trick of machine learning. Machine learning in this system is going to gather the information and data which is required for AI DRM to make decision. For example, we have a DRFP concept. If you guys are familiar with RCS2 standard, there is a DRFP, dynamic returning frequency planning, into this standard as an option, which is going to change the frequency plan on the fly. So this is part of this AI DRM core. But how? It's getting the information and data from traffic pattern, protocol, and rates. There's a DPI, deep packets inspection. Peak time, congestion. For example, there's a cellular backhaul network in industrial area has a different peak time with residential. So all these things are learned over time by this machine learning. Signal levels are learned. Even the weather forecast can be inserted as an input to this machine learning. So we will have a forecast, for example, there is a snowstorm next week in Montreal area, and our teleport X is going to be affected to this much dB rain fate. So this can be predicted and mitigated in advance. Mobility patterns. It can even learn the patterns of the uncertain mobile objects. For example, if there's a train, we know the train pattern, but if there's a car, we don't know. But over the time, it can learn that. For example, this person always driving to the office and coming back at this time, so it has to hand over around this time to the other beam. These are all learned. Failure, traffic interruption patterns, all these things are things that can be learned by machine learning, and even more into that, deep learning. As a subset of machine learning, we can go to deep learning for some aspects, especially for frequency planning and interruption patterns and mobility pattern, to even use unsupervised trained data sets. You may say, okay, it's a very long algorithm, it requires lots of CPU power and all these things. I would say no, because in the other applications, the input to the deep learning, there are many inputs to that, and many things many streams of data have to be learned. But in the satellite, it's not like that. You see, we are facing 10 or 20 or 30 measures and variables. So our variables are not so huge, and our criteria is more, I would say, defined and restricted. So the algorithm is not going to be really long, and deep learning is really applicable to such an application. This is the layers of this mechanism. So we have a physical layer. The physical layer is to the satellite. So there's a low-level scheduler to manage that. There's an intermediate layer for the managing the dynamic rate and SLA. And at the end, the upper layer is an API, and a standard API to the 5G core, which we'll explain in the next session. This is a way to actually adapt to this new environments. But why 5G? Okay, we said there are some advantages of using AI and ML, but what 5G will bring to us on the ground segments? First of all, everything that everyone is complaining right now on the satellite operators is the interoperability. So the satellite operator is pushing on interoperability, and we don't really have a standard for commercial satellite. We do have DVB, which is for broadcasting, but the others, there's no SatLab anymore. The only standards that we see these days that they are being followed are 3GPP. So we have 3 revisions for satellite in 3GPP already, and DIFI, digital IF. So it is probably the only way to make these networks interoperable. And it's very important for risk management because these networks are huge. And the satellite operators cannot really count on only one vendor to work with. So they want to be able to use different vendors. If one vendor goes bankrupt, what happens to them? So these huge satellites, there's a big risk factor into that. So 5 years from now, we expect that this standardization will happen. It also opens up a new market because it's going to the 5G, so it will get some of the applications of the 5G and 6G world. And it's a cost reduction. The 5G core is already ready there, so the CapEx must be much lower, and the OpEx is also practiced to be much lower and more stable because these networks have been there for a while and they have been used, bugs have been fixed, and all these things. So, and finally, the last but not the least is using all the new technologies on the 5G that for them is not new, but for us is really state of the art. For example, everything about mobility, IP handover, We'll get to that. Ciphering, deciphering, all these things are advantages that we can use from current 5G core. But how? Okay, it's been a year that everyone is talking about 5G, but how do we want to do that? Just a buzzword or no? There's a way to do it. There are three main approaches to do that. First of all, using a satellite as a carrier. So encrypting and encapsulating everything on 5G, including the network layer, communication layer, and traffic into the satellite encapsulated and physical layer and pass it. So the satellite works as a, let's say, a carrier, a pure carrier for the 5G network. It has two big issues. First of all, the bandwidth wasting. We have to have all the overheads of the 5G and carry it over the satellite, which is not really needed. So it's not going to be efficient. The second one is some commanding, some handshaking does not work as it expected. So there are some restrictions to what we expect from the 5G features. The second idea, which is mostly mentioned for the LEO satellite, is having the a 5G waveform on the satellite. Even putting making the satellite as GEO B. So I don't say it's not possible. Of course, it's possible for some cases. There are some companies already doing that, having some proof of concepts, but the market is going to be very specific. It's not multi-market. It's not applicable for all orbits and all satellite constellations. So it will be very limited use case. I don't see it for the internet and broadband. It's not likely that it can do a high throughput there, and it's not likely to be very efficient. The third approach is having hybrid split level, which we like it. So combining the best of two worlds, the satellite and the 5G. We know that the physical layer of the satellite is adjusted and customized for the satellite to be the most efficient. But also the 5G, the control layer and traffic handling and all the features on 5G are very advanced. So what we are talking about right now is transcoding. So merging these two together, keeping the satellite physical layer and having an interface to the 5G and translating all of the control protocols to the language which is understandable for low-level scheduler and the resource manager and transport layer of the satellites. There are a couple of advantages into that. First of all, it's the most efficient way to do that. It's going to be multi-markets. It works with both classic satellite and new markets. But more importantly, it can work, this idea can work with any physical layer, because we are going to translate that to the demand on the ground, on the physical layer of the satellite. So the physical layer of satellite could be anything, and there is an interface, and this interface is going to work with the upper layer 5G core. So what's the 5G-based space bridge VSAT new radio? We are going to adopt the control layer. Of course, as I said, we are going to follow the third solution as from what I explained in the last slide. So adopting 5G control and network management layer, combining the control and authentication layer of a 5G. I'll explain in the next slide, but we will have a UT to have an emulated user equipment to connect to the 5G core network. And we will get all the advantage of the 5G features, multi-service system, mobility, handover, ciphering, deciphering, encryption, and global orchestration, which is the most important thing to me. This merging system will allow us to be 5G, 3GPP standard, ground segment with the optimized transport layer of the satellites. As you see in this picture, we will have the GEO B of the satellite. They're going to be authenticated and managed by the MME. Also, the SpaceBridge new radio, the UT has an emulated U, which is going to authenticate to the MME as well. So we are not going to have two completely separate networks. As here, this is split level. On the lower layer, the VSAT user terminal is going to log in and authenticate to the physical resource of the Space Bridge VSAT new radio, and on top level, over the control layers N1, N2, and N3 is going to connect to the core network of the 5G. There is a standard API. As I said, this standard API allows the interoperability and allows this to be applicable to different satellite technologies. And this is a way we see it as the fulfillment of the global orchestration. So let's say there is a big network. Cellular networks are usually bigger than the satellite. So satellite is a subset to them. So the satellite networks could be just an addition to the current network, and the operator is using the same orchestration. But okay, there is another means of transportation, there is another infrastructure, but the orchestration is the same. The OSS PSS is the same. So this is a big advantage into that, and it really allows to reduce the OpEx on these systems. Okay, what are the markets for that? As I said, for the new LEO constellation, there are some constraints for some markets because there is no cheap terminal. There's a phased array antenna, it's pretty expensive. The terminal is mostly a high-grade terminal because of the handover, because of the multiple modulators and the modulator requirements. But here is not the case. These GEO systems, you can have a massive industrial IoT. You can have very, very cost-effective terminals, consumer market, internet. So you will have all the classic application of the GEO carried to this with more flexibility and better price because we are lowering down the CapEx and OpEx. In addition, there are new advantages for mobility, very high capacity mobility, which is a new requirement in the market. For example, in-flight entertainments, cruises, trains. The capacity which is expected today is way above what it was expected 5 years ago or 10 years ago. 10 years ago, there was no such an in-flight entertainment that much. So this capacity requirement, probably the best solution for them is the SDSN unified satellite systems, because not only it can provide the capacity, but also it can manage congestion and can manage the follow me beam chasing and handover if it is needed. So backhauling, trunking, and many new applications, as I said, this system is going to be 5G standard, 3GPP standard, so it can get some of the applications and hybrid models with 5G and 3GPP. And as I said, the last but not the least, defense and military applications. Military application has always been bread and butter for satellite systems. So probably one of the most stable money-making markets for the satellite is military and defense. So this solution is really, because we are talking about lightweight terminals, portable terminals, we're talking about the quickly deployed terminals, and all these things are really the market for the SDSN GEO satellites. So that's it. Thank you everybody for listening. I'll pass it to you, Richard. If there is any question, I'll be happy to answer.
Thank you, Amir. I'm just going to join you on screen for this Q&A. We have got some questions that come in. They're quite generic though, so some of them you might want to answer, some you might not. First one, you've talked a lot about the use of AI. What security issues can that cause with the use of AI, and how do you compensate for that? You're on mute, Amir.
Oh, sorry. Yeah, I always have this mute issue. Sorry for that. So, yes, a syndrome, I think. It's a very interesting question, honestly. The security issue for AI, we have to talk about two things. The security issue of the infrastructure, so, and management and traffic, a control layer, traffic layer management, which with this AI, it could be even worse because this AI is deciding about assigning capacity to these things. So for traffic, of course, we're still using ComSec, like an encryption, AES 256. There is a ciphering encryption on the lower layer, which is could be considered as an equivalent to TransSec. But there are mechanisms to secure the actually the control layer, because at the end, this AI is making decision based on the data it receives. So the control layer is going to be over a VPN, over AES 256, definitely, even if it is not on the over the satellite. If it is over the satellite, it's going to be, as I said, something on a BB frame encryption. The VPN was going to secure that, because imagine the AI core gets a very wrong information about the power and decides something which is pretty wrong and drop all the terminals. So we don't want it to happen. This is a first security issue. Security encryption, that's a solution for that. And we'll have some mechanisms, for example, not any terminal which is not allowed in the network, the MAC would be rejected and all these things. We don't allow fake web MACs and all these things. So it's a big subject and it requires probably another webinar for that. But in addition to that, there is a risk on using uncontrolled trained data. So unsupervised trained data on deep learning is a very challenging subject. It requires several discussions, several tests, POCs to get there. I'm pretty sure for the first phases, we are not going to deep learning and unsupervised data.
Okay, we have a question that's come in, and I hope I've pronounced his name right. So it's Mohammed Garsim. He's asking, 5G and AI will add more delay, as we already have 500 seconds as a delay for uplink and downlink. What do you think?
The 5G and AI will not impose more delay to the network. You know, there is a delay from the network. When we are talking about the GEO satellites, of course, light speed over 36,000 kilometers, so the round trip delay is going to be around 500, and we have to add the networking delay to that. When we are talking about LEO, it's going down to around 30 milliseconds, 35 milliseconds, something like that, because much closer. The 5G and AI is not supposed to add, the AI is not supposed to add delay to that, because the changes are mostly in a logical layer just to provide a better capacity and better power for the traffic. So it may even lower down the jitter because it prevents the congestion. So by this congestion mitigation, it provides a better jitter and delay for bandwidth on demand environment. But what about 5G? If we do a 5G over satellite and we use a satellite as a carrier for 5G, I will accept this argument that we're adding to the delay. But we are not doing that. We are merging our system. So it seems like today we are getting a traffic, we are encapsulating, we are merging our encapsulation layer, because, for example, the GSC that is very common in the market is pretty similar to encapsulation of the 5G. So we are merging these together. We are not adding any more layer. We are still having the same number of layers. So what I expect, the data processing of the 5G, because of the SDN, software-defined network, has less delay. So what I expect by going to 5G, we can even get a better result on delay overall.
Okay, we've had a question come in from Crispin Littlehales. What is the timetable for adoption of the SpaceBridge solution? How long does it take to get the system up and running smoothly?
Oh, there is not only one release first. So these satellites are expected to be ready 23, mostly end of 23, 24. So our timeline is aligned with that. So our, because it's a phasing, it doesn't mean that, let's say all features are coming together and no one can claim that. So the timetable is some releases in 23 and the full solution in 2024. At the time, the satellite will be ready.
Okay. Question here. With the complexity of LEO constellations and ground segment issues, why is everybody racing to get involved with LEO?
Oh, this is a huge subject, and there are many people talking about that. First of all, there is a big marketing on the new LEOs, and all the, let's say, millionaires around the world is very enthusiastic about this market, because on paper, it was a great solution for everything and multi-mission and getting rid of the interference on the ground and getting rid of the actually other constellations on the satellite. So I believe there was a phenomenal advertisement over the LEO, which attracted all the investment. There's a huge investment on these LEO constellations. But what we see after 3-4 years, we see that the complexity of the network was underestimated. So I can name many of them. It is public information that those were the earlier in the market, were started first. They have none of them has met their targets on the cost and time. So this is a bad sign for the investors. But anyway, according to the reports we get, for example, NSR reports, 3 or 4 of them will survive and they will be successful in the market. But I think marketing was great, but the initial estimate was not really great on these systems.
Well, Amir, we've got lots of questions coming in now. There's another one coming here. This is from Paul Sandoval. How dynamic SD satellite needs to be? I think they are reconfigurable, but not really dynamic if we define dynamics per short unit of time.
There are 3-4 layers of the virtual to physical attributes to be configured. So the virtual attributes are real-time configuration. Just if first, hello, Paul. Paul used to be my ex-colleague in Spacebridge in Advantic at the time. I don't know, more than 10 years ago. We have not met for 10 years. But just to answer your question, let's say you want to change the power. This is instant. This is real time. So some attributes are dynamic and are virtual, or we want to change, for example, the assignments of resources. We want to change the returning frequency plan on a beam. All these things are dynamic or real time. But changing the beam size, for example, changing the spot beam to wide beam, this is going to be a little bit in shorter pace. We expect around, as a scale of minutes, less than 10 minutes. So the physical reorchestration will be done probably every 10 minutes maximum. But the other attributes are going to be real time. As I said, there are 3-4 layers, and the repetition of change on these 3-4 layers are different.
Okay, we've got a question coming here from somebody called Johnny. What is Spacebridge doing in terms of the initial steps to support 5G and AI with its hub ground system?
Sorry, I couldn't hear you very well. Could you repeat it again?
Yes, sorry. What is Spacebridge doing in terms of the initial steps to support 5G and AI with its hub ground system?
Okay. The very first step, actually, we are working with the 5G core network partners. So we are, as I said, we are not going to learn everything from scratch. We are getting partners into this spectrum. The very first thing on the 5G is developing the this API and defining the real meaning of transcoding and hybrids. So for us, because the physical layer is already there, we are not changing our physical layer that much. Demodulation is there. We are going to adjust a little bit on our encapsulation and decapsulation layer and developing the API to work with this partner as a 5G core. With the AI, we have started using AI a long time ago. On Wave Switch, we are using some machine learning and AI into that. But with the AI, because the software-defined satellite network, we do have information, but we don't have it ready right now. So we are developing this core to be working with the API, which is provided by the satellite operators. So the satellite operators, they have a fast link, they provide us with an API, and we are trying to actually make our intelligence core to command that API for that dynamic resource management.
Okay.
These are the first two steps.
We've got an anonymous question coming here. It's quite an interesting one. Are there other providers who are offering the same solutions as SpaceBridge?
I think tomorrow they will claim that. So, you know, the 5G has been there. The 5G buzzword has been there for almost a year. Of course, we have competitors, vendors of the ground segments, but I think the idea of how to do 5G over the satellite, especially over the GEO, because LEO, for example, we have a space agency, European Space Agency program, ESA program, to have GNode be on the LEO satellites. This is already actually program on the table. Everyone wants to contribute. But we are talking about GEO. We are talking about the new SDSN satellites. I have not heard a strong statement that the solution has already been decided and they are going to provide that. There was discussion how to do that. I've not heard that, but you know, we are competitors. We'll not always release information to each other.
Right, we have a question here. It's an interesting one. Are ground segment companies like SpaceBridge having to hedge their bets between LEO and GEO?
It's the answer to this question could be very simple as is. Some modules between LEO and GEO are similar, some are not. So if you want to have a unified system to do the LEO and GEO at the same time, it means the orchestration is probably mostly the same. For example, we don't have a constellation management that we have on LEO on the GEO. There are some attributes into them. So we are trying to make a unified system to use as much as possible the modules for both. But this is part of, because our focus right now is on the SDSN, but the LEO actually is a side activity on that, in a parallel activity on that. We are trying to merge these two activities together. So what I would say as a final solution, there would be modules that are similar for both, and there would be modules specific for each one.
Okay. We've got a question here in from Ivan Reuter. The question is, how realistic and feasible is the entire cloudification of a 5G satellite hub, including the modulation and demodulation using L-band over IP, in order to eventually avoid having any hub equipment sitting at the teleport?
Oh, it was many questions. It's not one question. First of all, how feasible is using 5G standard? I think it's pretty feasible if we use transcoding. Of course, the other solution work, but they're not really efficient, or they're not really, they're pretty specific to a specific market. So transcoding is pretty, I would say, low risk approach to do that. Wi-Fi standard is they're having actually L-band over digital. So having digital L-band over fiber is there. It's not part of the 5G. It's mostly part of the RF section. And this is a demand today. We are going to do that. Regarding any external equipment, there is no external equipment beside digital IF. That's all the ground segment vendors are going for that. We are doing that too. But beside that, there is no specific hardware requirement for that, because the SDN software-defined network has already been there. We are experienced with that. We're working with the data processing. We do have our own data processing core like the others, but now we are using the data processing core probably from the 5G partner. So we are not adding any uncertainty to this spectrum.
Okay, I think that question is so long that perhaps that's one for a follow-up afterwards. And also, previously, the question that Mohammed Qasim asked you, he's come back with more discussions about the delay. So that's one to follow up on afterwards. We have one more question come in, and this is from your old friend Paul again. And you mentioned GEO satellites of 2,000 kilograms versus 5,000 kilograms. What is the trade-off? Perhaps less life expectancy in orbit, i.e. 8 years instead of 15 years. Have you got a view on that?
The trade-off, honestly, first of all, I'm just saying my idea. These are not the information available to the public right now. The digitized domain, you know, part of the industry 4.0, which started from 2016 and the target is 2025, is getting rid of hardware and analog as much as possible and going to digital environments. And of course, satellite is doing the same thing. So the digitization is the advantage, and digitization is the key to make these satellites more, I would say, lighter and more capable. So what I would say, the trade-off of having a lighter one, of course, we will have the lifespan of the satellite. I can't really claim, I don't have this information that the lifespan of these satellites are less or more. But the point is that with this approach, they're definitely faster to be built. So smaller satellites with digital payload, they are much faster to be built, and they're much faster to be validated and tested compared to the traditional satellite that we had all the RF components into that and all analog devices and transmitters and all these things. So what I would say about the lifespan of satellite, I don't really know. I don't have the information. But regarding the time to market and manufacturing time, and of course, launching would be much cheaper when it's lighter. But time to market, I think they really claim 50% less. I don't say it is exactly 50%, but it's much less than what we have today.
Well, Amir, we haven't got any more questions that have come in. So I think we've reached the end of today's webinar. I'd like to thank you, Amir, and SpaceBridge for a very informative session. I'd also like to thank all the attendees for taking time to join us today. Recording of today's webinar will be available shortly for download. So thank you again, Amir.
Thank you so much for hosting this webinar and all the audiences. I hope it was useful, and have a great morning and afternoon to all the cameras around the world.
Thank you very much.
Thank you. Bye-bye.